All right, guys, here we go. In this video, we're going to introduce you to something called kinematics. Now, I'm going to introduce you through some graphs that you may be familiar with. All right, so in these graphs, you can see, hopefully these look familiar. The first one is from our car lab, right? You may remember that in the car lab, you ended up getting two graphs that were pretty linear, right? Because the cars had a pretty constant speed. We learned that speed or velocity was the slope of the displacement versus time graph, or the position versus time graph. All right, the one over here on the right is from the ball drop lab, right? And we found that we got kind of a quadratic curve there, okay, that as the ball fell, it got faster and faster, and so the slope, the velocity, needed to get steeper and steeper and steeper. Now, you may remember from math class that when you had a linear graph, you could write that as an equation, right? You could write that as y equals mx plus b. And when you had that y equals mx plus b, you could put any x into that equation and it would give you the resultant y. So it stands to reason that if we have information about the time and the position, that we should be able to put this into an equation and we should be able to predict the position at any time, as long as this continues on the way that it is. The same thing with the ball dropping, right? A quadratic, you can write an equation for a quadratic. It just has an x squared in it, right? You can find x-intercepts, you can find out the stretch or the squish. You can set up an equation that is a quadratic equation. And with that, you then would be able to predict what would happen in the future. So in this next slide that I'm going to show you, we're going to introduce to you three equations. These are called the Kinematics Equations. What they do is they give us a way to deal with these things, with position, with speed, with time, with acceleration, that will help us to be able to predict or say what happened before regarding a certain situation, given that we know some data. Here, come, let's have a look. All right, so you'll see the three equations here. The first one is v equals v naught plus at. You got x equals x naught plus v naught t plus 1/2 at squared. And then we've got v squared equals v naught squared plus 2ax minus x naught. Now, you'll notice that anytime I see the zero, I say naught. I think that comes from the English word for zero, the British word, UK word for zero. They say naught for zero. And what that is for us is that is at time zero. Anytime you see the little subscript there, just like this one right here, or that one, that's talking about some initial quantity, all right? Now, most of these variables you're probably somewhat familiar with, right? If you look at these equations, you'll probably notice that there's actually not that many variables. There's 6 different variables in these equations, right? You've got an x naught, you've got an x, you've got a v naught, you've got a v, you've got an a, and you've got a t. Those are the only variables that exist. Now, you may ask, well, why do I need 3 equations? Well, let me explain. 3 equations are helpful because if you'll look at the first equation up at the top, what does it have and what does it not have? You'll notice that it doesn't have any x's in it. And so if you don't know anything about your positions, you can use this equation to help you find for some missing information. It won't tell you the position, but it will. If you have 3 of those other variables, you can solve for another one. The second one, you'll notice, does not have v in it, okay? And we'll identify what those variables are in just a minute. But again, if you don't have that v, you can use this equation. The last one doesn't have t in it. And so if you don't have t, then this one is a good one to have. Now, that is if you don't have it and you don't need it. Obviously, if you're looking for t, then you don't want to use the last equation. I'll give you some examples in a minute. Don't worry too much. All right? Now, let me go ahead and identify these variables for you. All right? We've got x naught. That is the initial position. Okay? Now, the initial position allows us to put in where our starting point is. Now, our starting point could be the very beginning of the story, or it could be when the ball is up at its maximum point, or it could be some other point along the path of whatever's happening. But we can identify a single point as our initial point. That's going to be our initial position. You'll notice there's also a v naught. That's our initial velocity. I can spell, I promise. Initial. And I can't spell, obviously. initial and initial. Okay, velocity. Now, this initial velocity is an instantaneous velocity, so it's the speed or the velocity that you're traveling at this initial position. All right, so those two should correspond together. All right, now the x is going to be our final position. Okay, now just like the initial doesn't have to be the very beginning of the story, the final doesn't have to be at the very end. And again, I'll show you some examples of this in a little bit. But the final position is just the point that we are interested in identifying as our final point. Okay? The velocity, the v here, is our final velocity. All right? So the final velocity is the velocity that we have at that final position. It's an instantaneous velocity, and so we can use whatever the velocity is at that point. Okay? Now, the last two you can probably guess: acceleration and time. All right? Now, acceleration, this, you'll notice that there's not an initial and a final. These kinematics equations only work if there is a constant or average acceleration, if that acceleration is not changing. If acceleration is changing, we cannot use these equations. All right? So be aware of that. You can only use it if acceleration is constant. You'll notice that all three of these have acceleration in them. So acceleration is kind of a big deal, and it only works if acceleration is constant. That's the one requirement of these kinematics equations. Now, if you're wondering where they came from, they're not magic. They actually came from our definitions for velocity, acceleration, and displacement. Now, if you'd like to see where they came from, I'll include another video in tonight's homework, which is completely optional. You don't have to watch it. But if you are interested in digging a little bit deeper and seeing where they came from, if you're interested in AP next year, it's probably worth taking a couple of minutes to watch the video just so that you can see how they're derived. Okay? The time is not a specific time. It's the amount of time that passed from our initial to our final positions, right? You've got your initial position, your final position. How much time did it take to get from one position to the other? Now, the neat thing about these equations is as long as acceleration is constant, you can use it. It doesn't matter if the object's changing direction. It will take into consideration the vectors, the positives, the negative directions, all that stuff, it'll take care of for you, all right? You just have to make sure that you put the right signs in and that you put in correct information. All right, so I'll show you how to use this now. We're going to look at an example or two. Let's go. Our first example here, practice with our kinematics equations. A toy car starts at rest and is released to roll down a 3-meter ramp. We're going to assume no friction or air resistance. If it takes 2.6 seconds for the car to reach the bottom of the ramp, what is the acceleration down the ramp? So what we want to do, and what I'm about to show you is going to be a lifesaver. This is going to be like your best friend over the next couple of days as we look at kinematics and over the course of the year. Anytime we do kinematics, all right, you're going to make a table. You're going to put down x naught, x, v naught, v, a, and t. Those 6 variables. There's always the same 6, all right? Now, we're going to write down the information that we have. Okay, I'm going to assume that my initial position is 0, and then it goes 3 meters down the ramp. So I'm going to say that down the ramp is my positive direction. So I start at 0, I end 3 meters away. That's what it says. It goes 3 meters down the ramp. Okay, now the initial velocity, it doesn't say explicitly, but it does say it starts at rest. So sometimes in these questions, you got to read a little bit deeper. And so we know that the initial velocity is going to be 0 meters per second. Now, I don't have the final speed. I don't know what the velocity is when it gets to the end of that 3-meter ramp. So I'm going to leave that blank for now. The acceleration, that's what it's asking for. It says, what is the acceleration? So I'm going to go ahead and write down A to remind myself that that's the variable I'm looking for. Now, last of all, I've got T, and it does give me 2.6 seconds to get to that 3 meters. And so all of this information is about that trip from the 0 at the top down to the 3 meters at the end of the ramp. Now, what you'll notice is that I have all the information that I need except for v. I should be able to solve for a. I just need to choose the equation that doesn't have v in it. All right? So if you look back at those equations, if you didn't write it down, you need to pause right now and go back to the previous page. Make sure you know what those equations are. All right? The equation that we're going to choose is the one without v because I don't have it and I'm not looking for it right now. And so the equation will be that x equals x naught plus v naught t plus 1/2 a t squared. And I know you're thinking, but Mr. Bauer, that solves for x. No. You can use this for any of the variables in that equation. You just might have to do a little bit of algebra along the way. So now we're going to put in each of those numbers, right? For the x, we're going to put in 3 because that was my final position. For the initial, we're going to put in the 0. For the initial velocity, we're going to put in 0. For the time, we'll put in that 2.6. All of these are in SI units, right? They're in meters, they're in seconds. So therefore, I can just put them in, and my result will be in SI units. So 1/2 times A times that 2.6 squared. So now I'm going to do some simplification. The 0 is going to add and it's going to go away. This 0 is going to multiply by the 2.6 and then it's going to add, it's going to go away. So really I need to do that 2.6 times 2.6 to square it. And then because of the associative and commutative properties of multiplication, I can do those in whatever order I want. So I'm going to square the 2.6, which is going to give me 6.76, and then I'm going to go ahead and multiply it right away by 0.5. So what I'm going to end up with is 3 equals 3.38a, right? That's the 1/2 times the 2.6 squared. Make sure you do the squared first. PEMDAS always rules, and then you multiply by the 1/2. Now at this point, all I have to do is do 3 divided by 3.38, and I get my final answer that the acceleration is equal to 0.89. I'll go ahead and round it, meters per second squared. Because the velocity is meters per second and the time is squared, then the units work out nicely to be 0.89 meters per second squared. All right, we're cruising. Let's go ahead and have a check at letter B here. All right, so letter B says how fast is the car going when it reaches the bottom of the ramp. So now I am looking for V, but I do have A now. This is still the bottom of the ramp. So this is the same initial and final position, but now I'm looking for V. Now at this point, I can use any equation that has V in it. Now, I'm going to avoid the one that has v squared because I prefer not to have to deal with squareds if I don't have to. So I'm going to use the equation. I'm going to do it over here on the right for letter B. So v equals v naught plus a t. So I'm going to solve for that v. I've got the v naught, which was 0. That's the initial velocity, plus the acceleration, which is what I just found. That's 0.89 times the t, which is 2.6. And so I multiply those, and I get 2.3. So the velocity is 2.3 meters per second. Again, everything's in SI units, so my velocity will be in SI. Not too bad, right? We're doing really well. Let's go ahead and look at one more example, all right? Come on. All right, you remember these little guys, little pullback cars? Yeah, we're going to do a problem with them, all right? So we got a pullback car. It starts at rest. And then when they release it, it reaches its top speed of 1.5 meters a second in a distance of 0.5 meters, right? That happened pretty quick. It sped up. It got pretty fast in that really short distance. So the question is, what is the acceleration of the car? Now, remember all three of our equations have acceleration in them, so it may be a little bit hard to figure out which one we need. So what we're going to do is we're going to make our table. We're going to go x naught, x, v naught, v, a, and t. What information do we have? It starts at rest. So I'm going to put in a 0 for the initial velocity. It reaches a top speed of 1.5, so it's going to be 1.5 meters per second in a distance of 0.5 meters. So let's say it starts at 0 and it goes to 0.5 meters. Now notice that the initial velocity is when it was at 0, and the final velocity is when it got to that 0.5. Now the question is, what is the acceleration? I don't have time and I don't care about the time. It's not asking for it. I don't have it. So let's use the one equation that doesn't have time in it. Can you find it? It should be this one. V squared equals V naught squared plus 2ax minus x naught. Okay? So we should be able to calculate that just fine. We can put in our final speed there, final velocity, which is 1.5. You'll notice I keep saying speed or velocity. Remember, when it's going in a straight line, if it's not changing directions or turning around, the instantaneous speed and instantaneous velocity are the same, except velocity would have a direction, in the positive direction going forward. Okay, my initial velocity is 0 plus 2 times a times x, which is 0.5, minus the initial position, which is 0. You'll notice if I do 0.5 minus 0, that's going to be 0.5 times 2 is actually 1. So that's just going to be 1a there. And then the 1.5 squared is 2.25. And as it turns out, I'm going to divide by 1, and I'm going to end up getting 2.25 meters per second squared equals a. That was not all that bad, right? Even though we used an equation that had some squareds in it, it turned out all right. It wasn't a problem, okay? Let's go ahead and look at letter B. That's going to be our final question here of our video. All right, this says, after this, it starts slowing down with constant acceleration until it stops 4 seconds later. What is the acceleration when it's stopping? Now, be careful here. It's very, very tempting to say, oh, times 4. But this 4 seconds is from after what we were just talking about. So this is starting at that 0.5 meters. So it started over here, it sped up, got to 0.5 meters. Now it's going to start slowing down. So this is actually a different scenario. It's a different initial and final point. And so I need to make a new table. All right? Don't get carried away and use the same table if we're looking at a different situation. So V naught V, A, and T. So now my initial position is going to be that 0.5 meters, right? That's where I'm starting the slowing down. And you remember, you saw that, right? It sped up, and then it started slowing down because of the friction. It was hitting the meter stick, whatever else it was that was causing it to slow down. We've got the final position. Actually, we don't know where it stops. So I'm going to leave that. The initial velocity is going to be that 1.5 meters per second, right? Because that's how fast it's going at 0.5 meters. And then at the end of that 4 seconds, it says it's slowing down until it stops. So my final velocity is going to be 0. I don't know the acceleration, but that's what it's asking for. So I'm going to go ahead, I'm going to look for A. And then time t is going to be 4 seconds. All right, now looking at those, what do I not have? What do I not want to use? It's that x right there. So I want to make sure that I don't use an equation that has x, because I don't have that final x and I don't need it. It's not asking for it. So if you look at those, probably your best option is going to be this one, the v equals v naught plus at. So our final velocity there is 0. Our initial velocity is 1.5 plus a times the t, which is 4. And you'll notice that I only have one variable there. It's going to solve it for us. So we're going to subtract the 1.5 to the other side. So we get negative 1.5 equals a times 4. So let's just change that to 4a. And then I'm just going to go ahead and we'll divide. We'll go that 1.5, the negative 1.5. Sorry. My calculator is not very happy with me right now. 1.5 divided by 4, and we get a negative 0.375 meters per second squared. Now, why negative? And don't you dare say because it's slowing down. Remember, slowing down is not the same thing as negative acceleration. It's negative acceleration because we started with a positive 1.5, and that 1.5 became more and more negative. It was getting closer and closer to 0 until it got there. So the velocity had a negative change. A positive change would mean it's getting bigger and bigger. It didn't get bigger. It's getting smaller. It's getting more negative. So therefore, the acceleration should represent a negative change there. All right, that's it. That's all you need to know about kinematics. I hope that was helpful, and we'll get some practice with that in class. All right, see you then.